For my final project, I did the Lorenz Attractor. The aim of this project was to program the Atmega328 to solve a non-linear ordinary differential equation. Now, the Atmega328 by itself is capable of solving any reasonable integer equation. For example, y equals 2x. You plug any number for x, your output is going to double that number. So you plug in 1, you get 2. Plug in 2, you get 4. Plug in 3, you get 6. The problem with the Atmega328 with the Lorenz Attractor is that the Lorenz Attractor is nonlinear and is chaotic. Being nonlinear means that whatever you input isn't proportional to the output, but it is still deterministic. So, for instance, in our original equation, it's predictable. You can intuitively see that plugging in 1, you get 2. You plug in 2, you get 4. With the Lorenz Attractor, it's not that obvious, but you will still get a number out of that equation, hence being deterministic. So that is one problem with the Lorenz Attractor using the Atmega328. Now, the biggest reason why the Atmega328 cannot compute the Lorenz Attractor with its current state is because the Lorenz Attractor, which was proposed by Edward Lorenz, was famously known for its chaotic behavior. What is chaos in mathematical theory? Well, chaos is basically any small change to the equation's initial conditions. So x, y, and z, you try and find your next position. Any small change will have a big effect on the final solution. Something as small as 0.00001. Just anything. This is what makes the Atmega in its current state insufficient to solve the Lorenz Attractor because the Atmega328 can only solve integer. There are plenty of sources on the internet that if you search the Lorenz Attractor, they will provide you code. I ran the C code on my Ubuntu virtual machine, and I attempted this project by just solving it using integer data types only, which means that if you have 3.14, what it will interpret as is just 3. You just chop off 0.14. Now, like I said, being chaotic, something as small as 0.00001 will have a big effect on the result. And having 0.14, which is chopped off, which is way bigger than the number I just proposed earlier, you can expect negative things to happen with the Lorenz Attractor, or unwanted solution if I put it that way. So one thing I noticed that if I try to play around with the numbers, I either get numbers that are so big that the computer will just return errors, NaN, which means it's a number that is not available that can be computed with your typical computer. Or if I try to get clever and try enough combinations and do some little bit of research about the equation, what happens is that there will be a pattern. And the pattern, although it is a pattern, but it is still the incorrect solution. There is just no way that I can see to compute the Lorenz Attractor unless you have a machine, which currently, even to this day, I doubt there's any machine that can compute the Lorenz Attractor just using integers, because these numbers would just explode to a point where it's just so big that it's not possible for a supercomputer today to take in all these values. That is why the Lorenz Attractor using a Atmega328, which is far from a supercomputer, far from a mainframe, can't do. So we have to solve this issue by implementing the IEEE 32-bit floating point. This is a representation, same thing. It's the same concept as scientific notation, but the IEEE 32-bit floating point is used in binary to represent big numbers and small numbers. Hence why we need it, because we need that fractional part precision from the IEEE 32-bit. Now, like I said, the more accurate the result is, the better for the equation. I could choose to run the 64-bit format rather than the 32. I picked the 32 for convenience. At the same time, the bigger reason is that the Atmega 328 is a low-profile microcontroller. So having 64-bit means much more computation, and I find that it's just not worth to slow down the Atmega 328 with 64-bit when 32-bit was more than sufficient enough to solve this particular equation, because I run it with the code that was provided from whatever sources that I was looking around, or I can just code it myself, just put in the equation and run the code and output it to a file. The equation is very simple. You got several constants. Three particular one is sigma, rho, and beta. They have a predefined value by Lorenz. You can change those values. That will change the behavior of the equation. Now, Lorenz used certain values that would produce a butterfly effect looking graph, which is the one that you're seeing right now. The fact that it is like a butterfly where it just kind of loops out of nowhere, like a massive trace. If you notice how wide the wings are on this particular graph, that is where the chaos come in. The chaos is causing this type of trace. Now, if it wasn't chaotic, it would produce what you call a pitchfork bifurcation, which is much more predictable. And Lorenz Attractor, in this case, with the values I'm using, is producing a nonlinear equation. But if you pick the right values, it can also become a linear ordinary differential equation. So it goes back and forth. It's not entirely nonlinear, it's not entirely linear. So we're going to solve that particular equation using the Atmega 328, then send it to the CPE301, which is a DAC, a digital to analog converter, which sends the signal to the oscilloscope to be graph. So we are going to try to produce this particular graph using a DAC. Now, this is the schematic that I drew up. We're going to be using two Atmegas. Each one represent an axis. So in this case, one Atmega is going to be X and the other one is going to be Y, since the Lorenz Attractor is a three-dimensional particular equation. So each DAC and with its Atmega is going to compute one of the axes, while the other one computes the other axis. Now, for my case, I just programmed them to be computing the same code. The only difference is one is for X, one's for Y. You can pick YZ, ZY, I don't know, any combination that you want to pick. It's not possible for the oscilloscope to graph 3 dimension. I'm not sure or aware of any oscilloscope that can do 3, but for whatever I was provided, I can only graph 2 axes, which was sufficient enough to produce a very cool looking graph. So in order for this to work, we got the CPE301, which uses the I2C protocol, connected to one Atmega and the other one connected to the other Atmega. The two Atmegas are connected to each other using one of the input and output port. Now, it is possible to have one Atmega connected to 2 DACs. The reason I didn't do it is because it required me to solder and cut some pull-off resistors that I didn't want to take the chance to do so. Due to resources being limited to me or taking the risk to do so. If I had plenty of them, I probably would try, but since this DAC was already not manufactured, but integrated onto a board, it was already set to these addresses that I couldn't change without doing some physical things to it, which I wanted to avoid. And in this case, I was fortunate enough to grab a second Atmega 328 and stick it to its other stick it to its own I2C port. So then I have 2 I2C ports to use for each axis for both DACs, and of course having 2 Atmegas. Components: Atmega 328 and the CPE301 DAC. The only interface I had to worry about is the I2C. Not much on the circuit side. It's very simple and straightforward. It's more into implementing it software wise. Now, of course, a lot of the microcontrollers today, they use integer values But there are certain situations like this that requires precision. So this is one of these important things to understand with microcontroller. And that was really the idea behind this project, is to implement floating points, because there's going to be some sort of application out there that requires absolute precision, and there's no tolerance for truncating the fractional parts out. So for my code, you begin by initializing the memory with the variables that you need, which is x, y, and z, its derivatives, and set up the I2C for the DAC. Now, to do this, to actually compute the Lorenz attractor, is to first solve the derivatives, because the derivatives determines what's the next value. Now, the derivatives are taken with respect to time. If you set time, the dt, as 1, the value is just so big. It's a scaled up version of the Lorenz attractor. It's going to go to trillion, quintillion, I don't know. It's just so big. So my choice was 0.001. So it's taking respect to time. Now, we're going to plug in the current initial condition, which is x, y, and z. I set one of them to be 0.1 and the other two to 0. You don't want to set them all to 0, or you won't get any useful values. It's just going to sit there with nothing being computed. Now, since this is the IEEE floating point representation is standardized, I didn't get exactly the same values compared to when the computer computes it. And the reason why is because there were extra measures taken after computing a certain number using IEEE. There were subnormal numbers. There were situations where in a normal computer, it will round the 4.99 to something like 5. So there are certain areas when I compare my results using the Admin Studio simulator to the actual results, but nonetheless, I was not computing like 10,000 values. 1,000 values was, 1,000 iteration of this computation of this particular equation was enough for what I was looking for. So there will be a certain degree of error because it's the base of the IEEE floating point, but it's good enough. So after you compute the derivatives will determine the next value of x, the next value of y, and z. And there's going to be negative numbers, and there's going to be positive numbers. All I did was just add them together. Now there's going to be 3 major operations that I'm going to need for the IEEE floating points: addition, subtraction, which I put along with addition, and the big one was multiplication. Now, addition and subtraction is very straightforward. You just got to match the exponents, and then you add the fractional parts and just adjust the exponents again. Normalize the exponents, normalize the fractional part, and then just adjust the exponents when you normalize it. Multiplication was a bigger challenge because multiplication, there are several algorithms out there, and one of them, the most common one, was the brute force. Just set up a loop and just keep adding it until you hit one of the values that determines when the loop ends, right? It's a running sum value. So we have 5 times 3, add 5 3 times. The problem with that is that if you have numbers are big enough, you're going to be adding a lot of numbers, a lot of iteration. And for the ATmega328, it's going to be using up a lot of its clock cycles for this particular operation, slowing it down too much. It's inefficient, absolutely inefficient. So what I did was that I implemented the Booth multiplication algorithm, a very popular algorithm that you can find any article on or any search on the internet. It's common. It's been used way back in the 50s and 40s to do computation. The difference between the brute force and this one was that this one was always constant, depending on how big the values are you're multiplying. So if I'm multiplying 25 bits by another 25 bits, then the most I will ever do was 25, roughly 25 to 30 shifts, or not shifts, 25 shifts, but like 30 cycles of operation, depending on how the algorithm goes when it reads the number. With the looping case, 2 to the 25, that is the worst case scenario. Whatever that big number is, it's just not good for a low profile microcontroller that I have. So the best choice was to take the time and learn the algorithm and implement it, and it will definitely work for the Atmega. I did try to use the multiplication by default that is for the Atmega on Admin Studio, it definitely didn't work because I'm working with 25-bit numbers, and the microcontroller by default is 8 bits. Like I said, I didn't go with 64-bit double precision because of overhead. I'm working with 32. We're on the boundaries of the Atmega not being powerful enough to compute these numbers, but luckily they were able to compute the numbers. So we're going to move along here, and once we're done computing the numbers, so in the case I pick the X and Y axis, we have two Atmegas. How do we sync them together? And it's very simple. Basically, it's just like a shell command. The code basically is you just wait for some inputs. So once one of the Atmegas has finished computing, all it does is that it sends a signal to the other Atmega to let it know that it's done. But at the same time, it's waiting for the other Atmega to send a signal back to it. Basically, the one Atmega taps the shoulder of the other. The other has to tap the shoulder of the original Atmega that was tapping its shoulder before. Because if the other one doesn't tap back or doesn't message back, the Atmega that was finished is not going to continue. It's just going to sit in a loop and waiting for the other Atmega. Once both Atmegas have finished computing, they should both send the signal at the same time, or whatever the case is. Both of them got receive some sort of signal in one of their input ports. That is when they have the go-ahead to move along to the next section of the flow, which was to convert this IEEE format to something meaningful. Now, what I did was that to get this floating point, I converted back from the floating point to a binary number. Now, since we have a fractional part, how do you represent that in binary, and how do you output it to the DAC? The DAC is a 12-bit DAC, so you get 4,096 integer numbers. And it doesn't take, definitely does not take binary floating points, okay? So what I did was that I truncate the fractional part out, which sounds like completely opposite of what my original goal was. You have to distinguish between the two here. When it comes to computing, the goal was to have fractional parts, okay? If you truncate it, obviously it just defeats the entire purpose of this project. But outputting it has nothing to do with the computation. Outputting it is just interpreting the data. And like I said, the DAC does not support binary fractions or anything of that sort. I don't even know what can be, but you have to put it into some kind of way to interpret that data. So in my case, if I get something like 1.54 something blah blah blah, I just truncate the fractional part. You're left with the 1, and I scale it to some sort of number. For example, I multiply it by 32 in my project. And the reason I multiply it by 32 is because when you actually run the test on the system for whatever computer you have for the C code, you get like 1.5, 1.6, 1.2.5, very small numbers that are not far apart, and you can't really distinguish them. So what I did was just multiply them, scale them up, and eventually you will get some sort of number that will be meaningful to the DAC. So once I get a binary number, I call my function digital to, digital to some binary number, whatever the case is. I think it's float to digital. Yeah, float to digital, convert that number, output it to the I2C, send it to the DAC. The DAC will send the analog signal to the oscilloscope, make sure the oscilloscope is set for X and Y, and that's pretty much it. Both Atmegas will be computing it. Of course, I have videos here. The first two videos is just showing with the Lorenz Attractor being graph X and Y, and the other three will be just X with respect to time, the derivative of Y with respect to time, and derivative of Z with respect to time. And that is it.